All right, on section AA6b-2, we're going to be solving exponential equations by what we call rebasing. So what we're going to start with is some stuff from last class where we were dealing with different exponent rules, which hopefully for a lot of you is a review, but not necessarily for everyone. So what we're going to start with, I just had the warm-up as different powers of 2, including negatives and zeros. And I want to talk about the negative and zero exponents and why they come about. So this is one of the things that came out of the investigation from 6b-1. So if I have something like x to the third over x to the fifth, if I were to expand that out, I have x times x times x. That's what x to the third means. And on the bottom, I have x times x times x times x times x. Now, if I start to simplify this, I can divide out x by x. The reason that I can do that, all I'm doing is multiplying on both the top and the bottom. So if that's the case, then I can start dividing things out. And I hesitate to use the term cancel out for when I make this line here, because what I'm really creating, anything divided by itself, is actually 1. And so when I start creating those ones, 1 times anything is itself. It doesn't change the value. So what I'm left with on the bottom is x to the second. And it has to stay on the bottom. So the 1, all those dividing out to 1, that became important because now that stays on the top. So what I have is 1 over x to the second. Now, one of the things that that leads us to is, the quotient rule, when I have x to the third over x to the fifth, that is the same thing as x to the 3 minus 5. That's the rule when I have the same base dividing. So that ends up being x to the negative second. Forgot the negative. So the negative exponent rule, basically this is where that stems from. So when I have a negative exponent, it is 1 over the base to the positive exponent. And a lot of people remembered the quotient rule where you subtract the exponents, but they didn't remember why that worked, or they didn't know why that worked. So when we're looking at this, this also has an impact on why zero exponents work the way that they do. Because if I have, for example, x to the third over x to the third, that is x times x times x over x times x times x. And once again, each of those divides out to 1. 1 times 1 times 1. So altogether, that just equals 1. Now if I use the quotient rule and I subtract my exponents, that's x to the 3 minus 3, which is x to the 0. So our rule then is that anything to the 0 power is going to equal 1. And a lot of people forget that, and I think the main reason they forget it is because they don't know why it works, so they can't work it out in their brain, so they go strictly from memory, and sometimes they think it's x or it's 0 or anything else, but if you know why it works, then you can figure it out on your own. So if I have, going back to the warm-up, if I have x to the negative, 2 to the negative fourth, that's the same as 1 over 2 to the fourth, which is the same as 1 over 16. So 2 to the negative third is 1 over 2 to the third, which is 1 over 8. 2 to the negative 1, I don't know why I skipped negative 2, I just did, is 1 over 2 to the first, which is just 1 over 2. Important to note, if something does not have an exponent, like if I have just x, the implied exponent is x to the first. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the fourth is 16. 2 to the fifth is 32. So that is the warm-up. And next we're going to move on to some solving stuff. As usual, I would recommend as we get to the new screen, you pause it and try it yourself, see if you can figure it out, and then move on. All right, so in class, we did this as kind of a whiteboard activity, and I had everybody look at how you would figure out how 2 to the x, or what x might be if 2 to the x is 256. Some people had some really good ideas because 2 to the x means you're multiplying 2 by itself a certain number of times. They multiplied 2 by 2 until they got to 56. So 2 times 2 times 2 times 2 times 2, and just kept doing that until they got to 56. Other people did 256 and divided until they got back down to 2. So what we're looking at today has to do with working with the same base. Right now, we have the same base, both of 2, and we have different exponents, x and 10. But if the base is the same and there's nothing else happening in this equation, then we can say that x equals 10. There's nothing else it could be for those two expressions to be equivalent. Now I have 2 to the 2x and 2 to the 10th. And once again, same base already. So my exponents, again, have to be equal to each other. So 2x equals 10, divide by 2, and x equals 5. As I move forward, same thing I'm going to check for is having the same base. So then I can set my exponents equal to each other and just set it up as a linear equation. 2x equals, whoops, not 2, sorry, 4x plus 10. Subtract 4x, so I've got negative 2x equals 10, divide by negative 2, and I have x equals negative 5. Again, same base, different exponents, but we know once again, even though they're different, they are equal. So 5x minus 8 equals 3x plus 10. Subtract 3x from both sides, add 8 to both sides. So I'm left with 2x equals 18. Divide both sides by 2, and I have x equals 9. So now I don't have the same base anymore. I've got a 4 and a 2. So I can't just set the exponents equal to each other because my bases are not the same. What I can do is take 4 and rewrite it or rebase it so that it has a base of 2. So instead of 4, I write it as 2 squared. And then I drop down everything else. Drop down to the x power and 2 to the 10th. And then one of the rules that we learned last time was that if I have a power to another power, then I multiply those. So this is equivalent to 2 to the power of 2x equals 2 to the 10th. And now I have the same base, and I can set my exponents equal to each other again. So 2x equals 10, so x equals 5. Now I have two unlike bases again, 8 and 4. A lot of people will make the mistake, or may make the mistake, that I can write this as 4 to the 2nd, but remember 4 to the 2nd is 16. So I actually have to take both of these back down to having a base of 2. And the limitations of this method really are that they have to be able to be rewritten, as well as you have to be able to recognize what those bases what bases they may have in common. So I'm going to replace the 2 to the 2nd, and then drop down to the x power. I'm going to replace the 8 with 2 to the 3rd, and then I'm going to drop down the 2x plus 1 for my exponent. And then I'm going to multiply my exponents. Now, when you do that, you need to be really careful because this is going to be 3 times the quantity, 2x plus 1. So I'm going to put parentheses around that because what I'm going to have is 2 to the 2x equals 2 to the 6x plus 3. So then, now that my base is the same, I can take my exponents and set them equal to each other. So 2x equals 6x plus 3 minus 6x. So negative 4x equals 3 divided by negative 4. And I've got x equals negative 3/4, or as some prefer it, negative 0.75. All right, so that is it. That's rebasing in a nutshell. Some things to keep in mind. You always have to go lower. Some people try to multiply this one by another 4 or something. That one wouldn't make sense. But try to make the smaller base bigger. That doesn't work because then you're changing just one side of the equation. If you change one side of the equation, you also have to change the other. So that doesn't help you to rebase. So you have to take either one of them or both of them down to a lower base. And not everything can be rebased, so it's important to keep that in mind as well. So that's it. When we get to 6C, when we get to that part of the unit, we will start into solving for the exponent in any situation, so especially when it can't be rebased. All right, have a good day.